Yes, good afternoon once again. I'm back to do this recording for you people to go through. I will just be very fast. We'll take question and answer during our next Zoom meeting, Zoom class. So I'll just share my screen to show you the 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 circuit I'll be working on. This circuit is very I will be okay. I'll be yes. This is the circuit I'll be working on now, and I'll be very fast. Okay, we have already put the components. Remember from this, from power source, we have gotten our AC power and then we have put it there. I've adjusted it to 12 volts according to the circuit diagram, 60 hertz, and the rest of it. Okay. We have put our diode. I recommended the virtual diode as I earlier stated. The reason is that it can adjust itself to suit the circuit parameters. And also, it allows us to even get the components that are not available in the parts section. So I have put the 1 kilo ohm there and then the 10 microfarad capacitor. So I'm going to now wire them according to the manual. We have our tutorial, our lab tutorial. So the first thing is when you are wiring, just click on one end and then join. Okay. I'm wiring the diode with the capacitor, and I'll move this to the center and then click outside. The moment you have that turn into a dot with cross, you are ready to wire. Then you click to make a perfect joint. The same thing with this one. Trying to connect the negative side of the AC power source, and then I extend this one down until you get that dot. That dot shows that there is a perfect joining. Then you need to bring your ground. And then, okay, I've got this. Then I'll bring I'll now bring my, I'll bring the I'll bring the oscilloscope from instrument. Okay, the oscilloscope is here, and I'm going to wire the oscilloscope uh, with the circuit. I'm going to connect the channel A and B to the two sides of the circuit. So let me move this here so that uh, okay. So I can make channel A to come here. Channel B will be wired to this point. Okay. Then, as I said earlier, it's a good practice to always ground your oscilloscope. Grounding your oscilloscope can help your oscilloscope from uh, misbehaving during simulation, can prevent your oscilloscope from misbehaving, from giving erratic behavior. So I'm going to place the ground source near the oscilloscope. I'm going to wire it. Okay. Now, when you click on the oscilloscope, wow, what is happening? Something is wrong. Okay. Now, I'm going to set all the basic settings on the oscilloscope. We have the 5 milliamp milliseconds per division. Then the other channel A and B will be set to 10 volts per division. 10 volts per division. And then the Y position will be on -2 minus 1.2. And that is on channel A. Then on channel B, Y position will be 0. And make sure that your settings are DC. And then we are using the signal over time, the Y over time base. So time, and then make sure that you also check your electrical rules. Don't forget, unconnected pin is one of the things you should check first. When you see 0 error, 0 warning, that means there are no unconnected pins in the circuit itself. So I'm going to simulate by click run. Okay. We can reverse this so that people can see. Can you see now? Can see that this is showing exactly what we want it to show. This is very, very interesting. If you want to reduce it further, you can probably reduce this time base. If you change time base, you begin to see different things. Okay. If you increase the time base, you see that it will become smaller. So you are permitted to make some adjustments so that you can see exactly how it is. And so this is something you can try from what I've done now. I believe you're able to. So this is smoothing the rectified sine wave using a capacitor. This is our figure 7. Figure 7, and it's very easy. Now you can uh, you can make some adjustment, as we said, and you can look through. You can go through the other things you can, in the tutorial. So we want to see if we can make some other changes to this circuit. You can see when it is 5 milliamp, you can see that it's a bit bigger on the screen. When it is 10, see that it's a bit smaller, closer together. And you can do the reverse of this if you are comfortable with the black background. And also you can still do reverse if you want the white background. So now quickly, I'm going to move to the next figure 8 on our tutorial. I want to look at that figure 8 using a Zener diode to get the desired voltage. That's what I'm looking at now. From this rectified, smoothing the rectified sine wave using a capacitor. From figure 6, we have used the diode to rectify a sine wave, and then we have used the Y position offset on the scope to generate the A and B channel traces. Now, we're now trying to look at how to smoothen it. To smoothen it is just like using a capacitor to smoothen the rectified sine wave. Now, we're going to now use Zener diode to get a desired voltage. Now, you will discover that we need to get a particular label, a particular Zener diode label BZV49C8V2. Now, if you want to get this particular one, you may not be able to get it in the real Zener diode section. So you may need to look at the generic Zener diode, and you can go through that and see if you can find it there. You can find it there. Quickly, I need to check something before I go to the next. Let me check whether my video is optimized. Yeah, it's optimized for high definition. Okay, now, so I'm going to start with this same capacitor. I will just do some addition. I will remove this, or let me just start from the beginning so that those who are, so I'm going to stop the simulation. For those who have not done that before, so they can have a better kind of understanding of the circuit. So I'm going to stop the simulation. From simulate, you can stop, or you can press F5 to stop. Now the simulation has stopped, and I can close this oscilloscope screen. When you double click on it, you will see it there. So I can close it. Now I'm going to start new. When I start new, now that's, I can actually save this circuit one. So it's good for me to save it. The same thing is good for you to save it. You can save as, don't save simulation data because it will make the file to be bulky. So just say no, don't save, and can just type circuit figure 7 of our tutorial. That's circuit figure 7. Okay. Now I've started a new circuit window, starting with the power source. As I said, you can pick power source. AC power can do it. And if you position it here, immediately you change it to 12 volts, 60 hertz, and then you say OK. The same way you bring out your diode, and I said use the virtual diode. Since we're not giving specific parameter or specific data of the about the about the diode, sorry. And then I'm bringing down the capacitor. You bring it from the normal basic component. You get 10. You can get 10 microfarad. 10 microfarad. Select it and click OK. And then as you drop it, you just right click and do 90-degree clockwise so that it can become like this. Then you can move it to a place where it will be free. And also we also need a kind of we need another 100 ohms. So you go to resistor, go to ohms, look for 100 if you can get. If you cannot get, okay, there is 100 here. Later, I'll be talking about tolerances. Tolerances are very important when you are selecting your component. Can you, from what you have seen here, you see that when I selected this, I choose 5% tolerance. We're going to do some. 1% is extremely, better. I mean, it's better, but they may not be available in the market, and they are normally more expensive. They're normally more expensive. So 5% is okay. Now 10% it's not recommended because it means that the value can swing 10% higher and lower. So that's the upper limit of the value. For instance, 100 ohms. When we do 5% of 100 ohms, we can have 5% added to 100 ohms, then 5% minus 100 ohms. So the tolerance will be plus minus 5%, and that will be the range of the value that will be used in the simulation, and also in real life when you are really doing the circuit construction. So we'll be talking about tolerances later during our lecture time. Now quickly I bring the Zener diode. From the diode here, I go to Zener virtual, and when I pick it, okay, I'm trying to adjust it. Now you can see that what you see here is something 5 volts. But when you look at the diagram that we are simulating, let me just show for the sake of showing. Yes. So this is the diagram I am trying to put the schematic in place before simulating. So don't forget, the first step is put schematics in place, capture the schematic diagram in the circuit window before you now simulate. Now I have put all this, I'll put all this, so it remains this diode. And when you see this BZV49 dash C8V2, it means the voltage, the breaking, the Zener voltage is 8.2. That is the what we call the breaking voltage. That's what so that is the voltage at which it will be able to regulate. That's the regulating voltage somehow. So let me continue. Let me share the. Let me go back to MultiSim. Yeah. Now I'm going to double click on this and I'm going to put 8.2 volts. And this is supposed to do what we are looking for. And then I also need a 1K. 1K. I need a 1 kilo ohm. From the resistor, I'll select 1K. And then I will drop it here. Then I will flip it 90 clockwise. And then I will adjust it here. So with this, I can start my wiring. I wire this end to this end to this end, this end, come here to this end. Now, this can come here. When you see the dot, it means there's a perfect joint. Then I can do this. You are seeing me here. This goes to the end here. Then all these ones can be dropped. Can be dropped here. Well, we'll see if we can do some labeling, or I can actually delete this one if I don't want it to be there. I can delete this maybe later, or I can come here. I can say value. I can remove this value. Okay, so it's like it's not. It's like it's not removable. Okay. Now with this, I will just put my. I will put my oscilloscope. I'll be showing you different oscilloscope later, but this is okay for our work now, for this demonstration. Okay, from the channel A, I drop this one here. From channel B, now what we are trying to emphasize is being able to capture exactly the circuit you have on your paper. So don't make mistake of putting another pin there. Now the next thing is the ground. Okay, I need to be able to put the ground so that my circuit will be complete. I put the ground here. and then I wire it. I can drop it there. It's okay. As also said, always try to also put ground for your oscilloscope to prevent instability. So now, after doing this, don't forget, always do your what? Electrical root check. And the most important one is unconnected pins. You may not bother about this. Just check unconnected pins. You can see 0 error, 0 warnings. So focus on unconnected pins. The moment any pin is unconnected, that means that circuit is not complete. But the moment there is no connected pins, then you are good to go. So now I'm going to double click on this. I'm going to move it so that you can see it as I start doing some adjustment. Okay. Let me bring this one down. Okay, so that it can be properly, and then so that you can see everything here. Now, from the settings, we need to do a proper setting of this oscilloscope. The time base is very important. It's set to be 5 milliseconds per division here. Make sure that your Y/T is selected. Then we come to channel A. It is 10 volt per division. Channel B also is 5 volt per division. You can see. So this is a little bit different from what we've been doing. Then the Y positioning on channel A is set. Y position, X position is 0. Then Y position, actually X position is having to do with the time base. Okay. Now, Y position is for channel A is set to be minus 1.6. Okay. So we have explained that you don't need to bother about 1.60, it's 1.6. And then the channel B, Y position is set to be 0. Set to be 0. And ensure that all these things are DC. And then if you want the white background, you can change it the moment you start simulation. So I want to start simulation now. I'll just go to simulate, or I can also click run here. Okay, now my simulation has started. Now I can do a reverse so that you can see clearly. So this Zener diode is being used to get the desired voltage. And you can see if I want to make it to be smaller, you can see that this doesn't work so well. Notice that for part of the time you have a constant voltage of desired value, but in between there are big dips. Okay, you may not understand this, but so when you use oscilloscope to investigate what is going on, as we leave the channel B where it is, but we can move channel A to measure the voltage across the capacitor. Okay, and as we do that, when we see from the oscilloscope picture, it is now quite clear. It will be clear for us what is going on. So as long as the voltage on the capacitor is larger than 8.2 volts, the Zener works fine. However, when the capacitor discharges below 8.2 volts, the Zener diode cannot make it more, and it stops stabilizing the voltage. That's what it means. So to make the circuit work, the voltage on the capacitor has to be higher than 8.2 all the time. So that is what will be addressed in the next adjustment that can be made to this. And so let me try to take it to 10 milliseconds per division. You see that it's becoming more condensed on the oscilloscope. So don't forget, on the time base, channel A, channel B. Now, these are the things that we need to take note of. So this is what we have been able to do today. And I believe that this is going to really help us. But let me quickly move it to what where we said to be. Let me stop the simulation. Sorry. So what I'll just do, I'll just delete this. I'll bring it to this point. Now, I will now do our run. You can see what is now happening. You can see what is happening now. So you can actually use oscilloscope to inspect at different stages. After just capacitance value, you may be interested in how constant the DC voltage actually is. On the 5 volt per division scale, you do not notice any deviation. But when you try to go higher, you will begin to see the trace will move off the screen. So, but since we are only in the oscillation around the constant value of 8 volts, we can switch one of our channel to AC mode. Now let's try to do that. This will remove the DC part and make it to look at some picture. So let's change to AC volts. Can you see? Okay. That is that. Take it back to AC. Let's look at this. You can see. So you can see when you change from AC to DC, you see some differences. You see what it looks like. Probably you can try AC, and then try DC AC like that. So so far so good. You can try the rest, and you'll be able to give yourself a lot of experiences. Trying it by yourself gives you a lot of experiences. Okay, so the next thing I'll be doing now is I will just take you through a few instructions. Let me talk about, or maybe that will be later. So I will post this for us to go through for now. Thank you very much. It's been very interesting. I would like to have your feedback, and it's going to be very, very interesting to hear from you and to allow you to make more contribution. Thank you very much.